All right. Hello, everyone, and welcome to our webinar on accelerating semiconductor packaging design with Quanscient Allsolve, or cloud-based simulations, specifically Quanscient Allsolve in this case. Before we get started, before we go into the housekeeping items and agenda, and then of course to the actual beef of the presentation, let's wait just a couple of minutes so we get everyone here live that is meaning to get live, so we don't lose everyone. First of all, for anyone who is on the minute here, I really wanted to thank you for being punctual. It's just with these webinar software and tuning in all that, it's always just takes a minute or two to get live. But I guess we can get started right now. So again, welcome. My name is Jukka Knutinen, and I'm the head of marketing here at Quanscient, where we have a cloud-based finite element method multiphysics simulation software. And indeed, today we'll be talking about accelerating semiconductor packaging design with cloud-based simulations. So I'll just go ahead and open this slideshow right here. So uh, just quickly, a couple of the important housekeeping items before we start. So first of all, I want to say that we have this opportunity, or you guys have this opportunity to submit your questions at any time from the questions tab that you see in the upper right hand corner. I think it might be upper right hand corner for you too. So at any point you have any question, even if it's right away, you can simply type it in to the questions. Rahul and I will see your questions, and we will be commenting on them, answering them throughout this event. And in addition to that, we'll have this live Q&A session at the end. But just want to emphasize that you can submit your questions at any time and they will be addressed. Another thing, this specialty is that we will be handing out some resources during this live event. So we have two documents, PDF documents that we want to give out to you guys, which will be uploaded to this materials tab that you can see on the right. So you can then download them for yourself to keep and to share forward as well. So yeah, kind of exciting stuff there. We'll touch on more about what those two special documents are. But yeah, you want to hang around for those. Now, quickly to go through over like who are we here talking. So indeed, my name is Jukka Knutinen and I work in marketing department. And with me, we have Rahul Nagaraja, who is an application engineer of ours, who will be doing the technical side of today's presentation. So I could invite Rahul over to this screen to introduce yourself.
Yes, thank you, Yuka. I am Rahul. And hello, everyone. And I'm an application engineer at Quanscient. I have been working here for the past 2.5 years. I'm a computational engineer by profession, and I have been fortunate enough to work on many different multiphysics applications here at Quanscient. Uh, I'm looking forward to showing you some nice things on semiconductor packaging today using Allsolve.
All right. Now, yes, before yeah, let's just quickly go through the agenda. What's going to happen in the next 56 minutes or so. So after these housekeeping items, after going through the agenda, we'll do a very quick introduction to Quanscient also for those who have not heard of it yet. And after that, I will pass the stage to Rahul to tackle the challenges in semiconductor packaging design today with these traditional, let's say, non-cloud-based tools. Just an overview of them, and then how cloud computing and these modern algorithms, such as the domain decomposition method, can be used to tackle them. After that, it's time for the sort of beef of today's presentation, which would be the IC package simulation by Rahul. So very exciting stuff coming in there. As I said, we'll do a Q&A section, this dedicated Q&A section also in the end. But yet I want to emphasize that you can and we highly encourage you to ask your questions at any time. And finally, we'll conclude with a 5-minute conclusion, key takeaway sections at the end. Now, about these handouts. So let's get into what those are and why they might interest you. So the first one will actually be about the it will be this executive summary of our API webinar that we had a few weeks back last month, and the other one will be this semiconductor white paper we did for Nordpack. And maybe you could, Rahul, tell us a bit more about these documents and why they indeed might be interesting to our audience here.
Yes, of course. So back in the spring, we worked on some two interesting cases for the NotPack conference. So we worked on two use cases. One of them was the packaging simulations. So basically, we simulated the mechanical characterization showing warpage and thermal stresses, and we showed how domain decomposition method can accelerate your simulation, and also how you can perform large parametrics. We will also go through this particular example today. And one of the other example we worked on was the inverse problem, where we used Allsolve API and integrated Python's optimization library in order to determine material properties from eigenvalue analysis. So the white paper describes both these use cases in much more detail, and the webinar handout talks about what was demoed in the last webinar.
Indeed. And yeah, again, as said, we'll hand these documents out during this event, during this live event in the materials tab where they will be available to download. Now, before going into the quick introduction of Quanza, and also I sort of just want to ask you guys, the listeners here, just throw this quick poll about whether you've heard of Quanscient before this event or not. So I'll make this poll visible on the screen now. So just answer yes or no. No judgment in either way. Just yeah, just we're curious to see whether or how many of you have been like just overall heard of us before this event. So yeah, I'll just give you a minute or so just to for you to answer. And we don't even have to make these results visible here. So getting some yeses, getting some nos. Don't know really what to expect here, honestly. Let's see. Yeah, let's maybe wait just a few more seconds so we can calibrate before going into this quick introduction. All right, the end results look like the majority have not, but no worries. I won't bore you with the details of exactly our company history, but just quickly go through an introduction. Indeed. So what we have is a yeah, cloud-based finite element method multiphysics simulation platform developed by Quanscient, and yeah, company established in 2021 in Tampere, Finland. So we're up here in north, but we have a international team basically around the world, and it is built upon the open source solver Sparse Lizard, which is developed by our CTO, Dr. Alexander Hallback. And yeah, we are working with companies or companies and organizations both in industry and academia are using Quanscient also for their simulations, multiphysics simulations in fields such as well, semiconductor packaging, which we are doing here, and of MEMS simulations also, and for example, fusion reactor design, so high temperature superconductor applications. So wide range of companies and wide range of use cases we have here. And yeah, just to sort of summarize the four key benefits that come from the cloud-based nature of the tool. So let's quickly run through those. So first would be the speed. And these will basically all of them be also what Rahul will touch on more specifically in terms of semiconductor packaging, but as a sort of general introduction. So speed is number one. So runtime from weeks to hours and days to minutes. This is what we have seen time and time again with our both with our customers and then with both of our internal benchmarks. And this basically comes from the fact that instead of solving the simulations on your own hardware, so with your laptop or workstation or whatever computer, it is solved in the cloud. So with basically next to unlimited computing capacity and RAM. And the speedups more specifically are enabled by the proprietary algorithms that we have created. And well, Rahul will touch on that also a bit more, go into the specifics. The other thing that goes hand in hand with the speed is the scalability. So indeed, as again there is this next to unlimited computing capacity, our customers are running up to 1,000 simulations at the same time with zero added computational time. And basically, this ability to run these massive parallel simulations, it really basically the creativity there is the limit. So you can do optimization studies, you can do parameter sweeps, you can run these manufacturer aware design simulations. So for example, one customer of ours did 1,000 simulation Monte Carlo study on these MEMS devices to basically to predict the yield and to calculate how to optimize that. So overall, this ability to run these massive scalability studies or these parallel simulations, increases product reliability, faster iterations in the products, eventually faster product to market. One way our customer put it is, when you have this ability to run more, you learn more about your product. So you better understand how your product works when you have the ability to run more simulations. And as said, this is something Rahul will touch on specifically in terms of semiconductor packaging later in the event. Just quickly on the flexibility side, that also comes from the cloud-based nature of a tool. So I'm sure everyone here has used cloud-based products. So as you know, there are no hardware investments there. So basically, the software and the hardware come in the same package. So the next to unlimited computing capacity I keep talking about is basically in the same bundle with the software itself. Then all the physics and features are also included in every plan. There is an unlimited number of users, so there isn't any the licensing bottlenecks or anything like that. Sharing a project, most of you have heard or used these Google Drive or Microsoft Teams or whatever. There's the Microsoft version of Drive. Those, so you know how the sharing is like. Also, there's this Python scripting interface in the tool. I don't know whether Rahul will touch on that, demonstrate how that works, but that's a cool thing nonetheless. Really gives this flexibility there. And then this usage-based pricing, but more about that maybe in the end. Now, this last thing is very exciting, so which Rahul also touched on already, is the automation part. So basically, this programmatic control of the simulation through the Quanscient API, which allows you to build these proprietary design workflows, for example, and just in a nutshell, remove these manual setups and repetitive tasks. So, as promised, I could actually go ahead and share this PDF summary with you right now. So, for anyone who is interested in seeing how this Quanscient API can be used, I will upload the PDF handout right now into the materials tab, and there it is. So if you go navigate to the materials, you should be able to download the PDF summary right now. And the recording for that is also linked into the event. So all of that is there. So feel free to take a look at that anytime after the event. Feel free to share it forward. And of course, ask any questions regarding that from us later on. And as a reminder, the NordPack white paper will come into the same address here in the material tabs. All right. Now, that is actually everything that I have before handing to Rahul. And actually, before handing off to Rahul to go into the challenges, we would like to hear from you. So we would like to just hit you with another poll, which basically is this problem that many people have been facing. And let's do this quick test here. So basically the question is, do you have to resort to simplifying your models to reduce the simulation runtime? And then there are 4 options: often, sometimes, rarely, or pretty much never. And in the same way as in the previous poll, I will give you a minute or so to answer if you'd like to. Again, this answering is anonymous, so the other attendees won't see what you respond So even though we can share the results, but you will only see the percentages there, not who answered and what. So yeah, already getting some yeses here. So yes, often, yes, sometimes. No one has yet said that very rarely or pretty much never. So that already tells us something. Yeah. Well, now we got our first very early, but yeah, I could. The minute is now here, so I could share the results. So yeah, this is what it looks like. Uh, more than yeah, almost everyone said yes, either sometimes or often. And yeah, to sort of complement that, there would be this question on run times. So basically, how long are the run times? So whether we're talking about minutes, hours, days, or very long run times of more than a week. So this question goes well hand in hand with the previous one. So this one is actually a multiple choice. So if you do many types of simulations, you can answer those all. But just to again sort of grasp where we are. So before going into the challenges that we will present. So again, getting a wide range. So we're talking minutes. Someone is talking hours. A couple of days here. More minutes. All right, let's wait 10 more seconds if we can get a maybe one more answer in the last minute before, or the 10 seconds before the minute is full. All right, seems like it has stabilized and the results look like this. So the majority is in the minutes and hours. That is what it seems like the most of you guys are dealing with. And then there was a couple longer runtimes of days. Perfect. So with that, I will close this poll and I will hand it off to Rahul to go through what we have seen based on talking with our customers that are the biggest challenges in semiconductor packaging design today, and how cloud computing and modern algorithms can uh, address those challenges. So go right ahead, Rahul.
Thank you, Yuka, for nicely setting up the stage for me. Let me quickly share my screen. Okay, so before we dive deep into the tool itself, maybe some introduction on the packaging simulation. So why exactly a packaging simulation is done? So basically, simulation provides some key insights into the mechanical and thermal characterization, and it has been used for a very long time, and rightly so. So it helps us understand what is the warpage produced during the fabrication process, what are the thermal stresses induced, and how efficient is the heat dissipation. And what the simulations also help in is performing design of experiments where you run the same kind of simulation for different values of parameters. So what are some of the challenges that we are currently facing? So we see that there is always continued miniaturization. This has also led to a lot of innovation. Over the past decades, we had system on packages, and currently we have advanced packaging. And one of the immediate bottlenecks, what it presents is uh, more and more engineers do not want to simplify their models because the insights that they were able to provide, although valuable, but they are not sufficient or adequate enough anymore. So they want to run the full fine scale resolution, preferably 3D simulation, including all the multi-physics. And one of the challenges with miniaturization and advanced packaging is we no longer have geometric symmetry, so we cannot really take advantage of considering half the geometry or quarter of the geometry in order to reduce the number of unknowns, which would result in shorter simulation runtimes. and it is becoming increasingly critical to resolve the vias and interconnects and determine the thermal stresses in copper pillars in the packaging simulations. Now, what does this or how does this impact the numerical simulations? So the first and foremost is when we consider the full-scale 3D simulation, we would have huge number of unknowns to solve for. And this means that the simulations would take much longer to converge. In addition to this, when you have large number of unknowns, you would naturally need a much uh, larger memory workstations are hardwares, and most often such hardwares are usually not available uh, with every engineer or researchers. And this significantly affects the design of experiments since you have longer simulation time and which requires much bigger machines to run those simulations. Usually we would have to resort to running a very few number of simulations, which would hinder how well of a result we can extract from simulations. Now, how does Allsolve come into this picture, or how would Allsolve offer to solve these problems? Uh, the first and foremost is we have a strong coupling of multiphysics. So all the physics are available under one platform, and the large number of unknowns and longer simulation time is tackled using domain decomposition method, which I'll go into a bit more detail in a short while. So with domain decomposition method, we can significantly bring down the simulation time of large scale simulations. And in addition to this, the one of the biggest advantage we can offer is running parametric sweeps in parallel. So this would naturally mean that you can perform your design of experiments at a much faster rate, thereby reducing the development time. And lastly, we have the Allsolve API, which you can use to extend the flexibility the Allsolve tool has to offer. You can use the API to integrate the simulation tool with your existing design workflow. You can do much more versatile pre-processing and post-processing of the simulation. And in addition to this, you can perform geometric sweeps as well using the API, and soon you can do the same in the user interface directly as well. So let's get into demo session. So I'll be showing the simulation of a thermomechanical physics of a flip chip ball grid array. So I'll consider solid mechanics and heat conduction physics and the coupling between these two. Um, we will see the thermal expansion interaction that happens due to the change in temperature when we bring down the temperature from stress-free to room temperature. And we will consider just a steady state analysis, so no time derivative part is considered. And as for the boundary conditions, we want to do a free warp-based simulation. So we are going to constrain all the rigid body motion. So all the three translations and all the three rotational degrees of freedom would be restricted. Going a bit more detail into the material and its properties. So we uh, have many different components in this ball grid array. So we have integrated heats, spreader, cut rails, and the flip chip die, and the ball grid array and micro bumps. But what I would like to bring your attention is to the highlighted material properties. So in yellow, so if you see that these material properties, they are dependent on the glass transition temperature. So in this example, so when the temperature is less than 260, we have a different value of coefficient of thermal expansion, and when it is above 260, then it changes. So I will show how we set such a material property during the demo session. So let's quickly jump to the tool itself. So what I have here is an imported step file of the ball grid array. So you can see the different components here. So I have the substrate in the green and the integrated heat spreader on top of it. And you can see inside you have the underfills and cut rails, and also the micro bumps here. So we have four um, main sections in the tool. So we start with the model where you work on your geometry, and the second is the properties. I have some predefined simulation setup here in order to save some time, because our focus of the webinar is to show the speed ups that you can achieve. So we wanted to allocate more time on that. So in the properties section, we have these shared regions. So here you can group different regions or volumes into a reference name, which you can then use anywhere in the simulation setup. For example, I have these solder balls shared region, and this comprises of the ball grid array and the micro bumps. And when I'm setting up the material, I can directly invoke this solder balls as the target region. And yes, so talking about the properties, so I showed earlier uh, about certain properties which were dependent on the glass transition temperature, and we use this if positive built-in function in order to set such material properties. So if you see here, I have the temperature field, and here it's the glass transition temperature, and depending on whether this results in a positive value or a negative value, the appropriate material property is automatically considered. And we also have some shared expression. These are basically just variables. You can define many different expression types, such as you can also define some analytical functions that you can use in your simulations. So for this simulation, I have two temperature values. One is the stress feed temperature, and I have considered it to be 150 degrees Celsius. And then the reference temperature is the room temperature, which is set to 25 degrees Celsius. I have this alpha substrate, which I will talk about at the end, why I have defined it here and how it can be used in parametric sweeps. Yes. Now let's jump to the physics section. So I wanted to show how to set up the physics. So for the thermomechanical simulation, we need two physics. One is the solid mechanics, and the second one is the heat solids. So both these physics are applicable on the whole geometry, and it defaults to the complete geometry here automatically. And now we add the interaction or the boundary condition. So for the heat solid, I apply a temperature constraint, and I select all the volumes of the geometry, and I set it to T end, because we want the at the end of the simulation, the temperature we want to have in the component is the room temperature, which is T end. Now let's set up the interactions for solid mechanics. So as said earlier, we want to restrict the rigid body motions, and this is done using three constraints. So the first constraint is I would select one particular point in the geometry and set all the components of the displacement to 0. So of the 6 rigid body motion, this would constrain 3 of them. Then I apply use YZ constraint. So here I select a different point and set the y and z component of the displacement to 0, and we allow the x component to evolve during the simulation. So this restricts the next 2 rigid body motions, and we have one more constraint to add, and I choose a third point and set the z component to 0, and the xy would freely evolve. So with these 3 constraints, now I am completely restricting all the rigid body motions. So this would allow us to run the free warpage simulation. So the last thing we want to do here is couple the solid mechanics with the heat solid through the thermal expansion. So the temperature field or the evolution of temperature would cause the thermal expansion, in uh, which would affect the displacement or the warpage. So the thermal expansion is applicable on all the regions. So I select all the regions, and for the reference temperature, I set the stress feed temperature, which I defined earlier in the shared expression. So now I have everything that is needed. All the physics and its interactions are fully defined. Now we can go to the simulation section. I have the mesh generation
Sorry,
already.
Rahul, there was a question quickly on the physics. So you demonstrated some of the physics, and a question we often get is that all of the physics that are available in the GUI, and what if some physics isn't there? So can you add your own physics into the software?
Yes. So we have a bunch of predefined physics already available, including the couplings with other physics. And if there are any other physics that are required, it can be done using the scripting API. So all you need is the weak formulation of a partial differential equation, and this can be directly implemented in the scripting API. I can quickly show when I'm running the simulation what the scripting API means. Yeah.
Sounds good.
Okay.
Perfect. And just a reminder for all the attendees here, whenever questions come up, yeah, just add them, ask them in the question tab. We'll address them uh, during the event. Thanks, Rahul.
Yes. So I have already generated the mesh, so we can quickly preview to see how the mesh looks like. Yeah. So I will not go much into detail on the different mesh settings, but yeah, there is some flexibility in how you can define the mesh. Um, this seems like a decently dense enough mesh to run our simulation. Let's go back to the simulations part. So I will add a new simulation, and I will select the steady state analysis as said before. And since it's a cloud-based tool, we have the option to choose among many different machines that are available. So you have the smallest machine, which is 1 CPU, 16 GB, and the largest machine with 32 CPU and 512 GB RAM. So I will select the largest node, and I'll call this simulation 1 with largest node. All right. So, and I set the mesh we generated earlier, and in the outputs, I want to visualize the displacement. And what would also be interesting is to see the displacement at the center of the substrate. So I would do an interpolation in the substrate region. And if you hover over the functions, you can see the documentation for that. And I want the Z component of the displacement, so I'll do component Z of the field U, and I will provide the point for interpolation, which is 0, 0 on XY and 0.85 mm in the Z direction. Yes. So now I have everything ready to run the simulations, and I will click on
Sorry, Rahul. Yes, good that
yes.
you got the simulation running. There was a question regarding the models. So in this case, was the geometry created in the tool? Was it imported? And overall, yeah, is it possible to import from other tools?
Yes. So in this particular case, we imported a step file. This was available with us. It is possible to create the geometry from scratch in the tool itself, but this is not a full-blown CAD engine. So if you have a very complex models, we usually have step files that we import.
Thanks.
Yes, and I also will quickly talk about this script. So it's auto-generated. So this is basically replicates what we have done so far in the simulation setup. So we have the mesh that is loaded, the fields that are defined, and also the boundary conditions and interaction. And you also see the weak formulation of the physics defined and the outputs that we added, the displacement field and the Z center. So you can enable the scripting mode and add your own customization to improve the flexibility in how you want to run the simulation or how you want to extract certain results. So now the simulation is running. You can check the status of the simulation in the logs. And here you can see that it has 10 million DOFs, which is a fairly large simulation. Okay. Now, while this is running, I can go back to the slides and talk a little about domain decomposition method. Okay, so what is the domain decomposition method and how can it help in acceleration? So in domain decomposition method, what we do is we take the mesh and we split it into multiple subdomains. So this value we can usually given by the user depending on the scale of the simulation, and you see that the the partition or the decomposition is not uniform uh, with regards to the size, but it is uniform when you consider the number of DOFs. So in the smaller subdomain, you probably have a denser mesh compared in the larger subdomain. So it considers the partition in such a way that the number of degrees of freedom are distributed uniformly. Now, what each subdomain is later done is sent into different instances of your hardware machines, and each of these would be solved separately, and the information is exchanged between the adjacent subdomains. And so since the large scale simulation is now broken down into smaller subdomains, it runs much faster. And I will pull up this graph from the NotPack white paper we did to showcase how powerful it is. So in the first point, this is a simulation which was run with just one node. So which means there was no partition, no domain decomposition used. And this also had close to 10 million nodes, and it took 64 minutes to complete the thermomechanical simulation. And in the next point, when we used around 10 nodes, we see that the simulation time reduced to 36 minutes. And if when we use 60 nodes, it was brought down to less than 10 minutes. This is a significant drop in the simulation runtime. I mean, even though the simulation runtime seems in minutes, this can give a huge benefit. Uh, I will set up the simulation with domain decomposition method and show you live how this is beneficial. So I will copy the same simulation. I'll just rename this as DDM acceleration. And here, instead of selecting the largest node, I will select the smallest node, but just use hundred of such smaller nodes. So now my whole mesh would be partitioned into 100 subdomains, and each subdomain would be run in separate instances. Uh, I will choose the iterative solver because it uses less memory. And now I'll run the simulation. While this is running, I also wanted to talk more on how DDM can help you in parametric sweep. So during the poll, we saw that most of them said that the simulation runtime was in minutes. So even if your simulation runtime is in minutes, uh, I I presume that you were talking about running one particular simulation. But what if you want to run a parametric studies where the same simulation would be run for different values of parameters? So let's take this hypothetical case. So I want to run this thermomechanical simulation with different values of stress free temperature and different values of coefficient of thermal expansion. So I have 5 different values for each here, and I want to run five sub simulations. And for each simulations, the corresponding temperature and thermal coefficient values are shown here. I will show you how to set such simulation, and we'll talk more
Could
about it
we,
once the setup
before that, there
is
were
complete.
actually a few questions. Let's address the at least the quicker one first. So basically, there was a question on how are the subdomains defined in the domain decomposition method.
Uh, could you repeat the question? How are the subdomains
So
defined in?
defined, yeah.
Yes. Okay. So it is primarily based on the number of degrees of freedom. So the partition tries to uniformly distribute these degrees of freedom equally or uniformly across all the instances. So, which is why you don't see similar size subdomains. So this is because you might have a denser mesh at certain regions and coarser mesh in some other regions. So typically, this is what is considered during the decomposition.
Then there was another question on the accuracy. So basically, this benchmarking. So have you tested the simulation accuracy versus answers or console, for example?
Well, we have a lot of benchmark and validation cases which you would find in the demo projects of our tool. Uh, for this particular simulation, we haven't carried out uh, any benchmarks. But for each fundamental physics and its interactions, we have a lot of benchmark and validation cases.
All right, thanks.
All right. So talking about the third simulation, I wanted to show the how to set up the parametric sweep. So I'll call this parallel parametric sweep. So I copied the previous simulation to create this, and now I go to the inputs and do a sweep over the stress free temperature. So I had 130, 140. So these were the different temperatures I wanted to run it for, and I convert them from Celsius to Kelvin. Then the other parameter I wanted to sweep was the alpha substrate. So this is why we defined the shared expression earlier. And here this was from 2 to 6 e power minus 6. Okay, so I'll keep this for running and I'll explain how this parametric sweep runs. So I have five different values for stress free temperature and five for the substrate coefficient of thermal expansion. So the parametric sweep now runs five sub simulation, and for the first sub simulation, it takes the first value of stress free temperature and first value of the coefficient of thermal expansion, and so on for the rest of the sub simulations. And the main or the biggest advantage we have in this parametric sweep or in such setup is all the sub simulations are run simultaneously. So once it starts running, I'll show what this means. So in this case, all five simulations are run at the same time. So you can say that it's embarrassingly parallel. And how can this be beneficial? So this can be a huge advantage when we are considering large parametric studies. So I have considered the case that we discuss in detail in the node pack here, where we had 10 different values for temperature and 10 different values for the uh, thermal expansion coefficient. And in that particular case, what we wanted to do was consider all the possible pairs these two variables could offer. So this would be 100 simulations. So because each had 10 different values. So even if your simulations are running in minutes, if you want to do such large parametric studies, this can significantly add to your simulation runtime. So running them in sequential is definitely not an ideal case. And this is where parallel parametric studies can show its power. Okay, now let's go back to the simulations that we started. So we had three simulations. The first one was the largest node, and you see that it is still running. And the second simulation was the DDM acceleration. And you see its status that it's already successful. So which means the simulation has already completed running. So you can see that domain decomposition can significantly reduce your simulation runtime. So this usually takes about 30 minutes for this particular case. And with DDM, it just ran in under 5 minutes. And with the parallel parametric sweep, so you see that now the sweep simulation has started for all the five different parameters we considered. You can see the status of these sub simulations while it is running. And with parametric studies, your typical runtime is equivalent to just running one simulation because all the sub simulations are run in parallel. Um, so we had some outputs where we were interested in seeing the displacement at the center of the substrate, and this would be outputted in the summary. Uh, Maybe we can visualize the var page as well. Let's see. While the visualization is rendering, maybe I can show some more graphs on this parallel parametric sweep. So we ran in the white paper, we had run 100 simulations parallelly, and we plotted the surface plot of Z displacement for all these 100 different parameters. So you can extract such key insights while running parallel simulations. It would be much faster, and you can run your design of experiments in a much shorter duration. Okay, so we have the
Actually, before,
visualization here.
sorry, sorry to interrupt. There was this astute observation from one of the participants who noticed that it actually ran faster now than in the benchmark. And the question was that does it mean that you regularly improve your product?
Yes, that is true. We have continuous development, so we release our product updates every 2 weeks. So that could be one reason. But also the setup is slightly different. Also, it's the same case. So in the white paper, I actually considered symmetry, but considered the same density of mesh. So it also had 10,000 million nodes. 10 million nodes. It could be the reason why there is a slight difference in the simulation runtimes.
All right, thank you.
Yes. So I use the war page filter here to see the actual war page of the simulation. So maybe a higher scale factor would give a better idea. And for the parallel parametric sweep, so you can now see that the sub simulations has started finishing, and you would soon see the status of that. Yeah. Okay. So while this is still running, maybe I can just show one last graph, one of my favorite graphs, which shows the speed up. So what we actually wanted to show was when you run your simulations, especially large scale parametric studies in sequence without using DDM. So you accumulate the simulation runtime for each parametric study that you do. And with also DDM, you already reduce the simulation of each uh, parametric study. So, and here what I have done is I have used DDM, but I still ran the simulation sequentially. So, and here, although you get speed up from the DDM, but you still do a sequential study, so it still adds up. So for 100 simulation, you still consume 1,000 minutes, which is a significant time. But when you run a parallel parametric studies, then your simulation runtime is equivalent to just running one simulation. So you get much larger output and more insights with a very, very short duration of time. Yes. Uh, well, I think this would take a little while to finish. Maybe if there is any more question while this runs, I could answer them, Yuka.
Yes, indeed. So there was one very good question about this more general question on who is responsible for the hardware infrastructure in the cloud. So is it as it is supplied by us? So who manages that?
Um, so we run the cloud infrastructure in Amazon Web Services. So the whole cloud infrastructure is maintained by AWS.
Yes,
We actually, yeah.
well, and basically on who is managing that. So in that is basically up to basically the agreement. So for example, there is this option of these private instances where the customer is handling their own clusters, their own instances with AWS directly. But in most cases with our customers, we sort of do that for them. So basically, it is a turnkey solutions, but for the companies who want even more control over the hardware, there is this possibility for these private instances. So, Rahul, I see we have 5 minutes left before time runs out. So, anything else you want to show here?
Uh, no, pretty much that's about it. I well now I see that all the five sub simulations has finished successfully. It's probably just wrapping up the uh, results. Yeah.
Yeah, gotta say, very very impressive results. And the graph of the, what was it, 640 times speed up never fails to impress. And actually, at this point, before moving any forward, if what you saw here, if this demonstration, what you saw, what you heard, sounds like something you'd like to explore further, I'll just put this one last poll here. So basically, asking whether you would just like a personal demo of the tool sometime after the event. So basically, if you say yes, we'll figure out a time to just explore how Quanscient also could work with your organization specifically. So what kind of challenges you're tackling right now, and what Quanscient can do to address those. So if that is something that you would be interested in, be sure to just, well, for now you can hit on the poll, and after that we'll take it from there. So just a few more seconds for everyone to answer before we move to the Q&A. Albeit we have just and before I forget, I will share the NORPAC white paper right after this poll. So just 10 more seconds so everyone can say what they have to say, and after that I'll put down the poll and share the NORPAC white paper, and we still have 3 minutes or so to address the questions. All right, there we go. And to the materials, I will, the same place where we have the API webinar white or summary, I will now upload the NordPack white paper. So as Rahul explained, it will have more details and it will have a more comprehensive setup, and more technical, more of a technical explanation of this case study. And that is downloadable now. Feel free to share that with your colleagues or anyone who you feel like. Now, with that, let's address this one question that we had here. So, well, how would you compare or differentiate your software from SimScale? That's one question that we had. What would you say to that, Rahul?
Yes, so we only use finite element method for all our physics and all our couplings, and I think that, yeah, the only common thing is we are both cloud-based multi-physics platform, but I think with SimScale you use many different discretization method based on the physics you are simulating. So in our tool, it's all the physics are finite element based, which allows us to do strong coupling between all the physics, which gives a much better convergence.
All right. Thanks. Now I see we have 1 minute 30 seconds, so I will use that to say what happens next. So what I didn't tell you is that what I will send you right away after this event is these speaker slides. So you will receive those in your email just a few minutes after we close here. And then on Friday this week, we look forward to gathering all of what we discussed here into this PDF summary of this webinar. So basically, you will get that to your email by Friday. So in a similar manner that we had the API webinar PDF summary, you will get one as a souvenir for this webinar as well. Yeah, with that, I would like to thank Rahul for the amazing presentation. I would like to thank all of you guys for showing up here live, asking your questions, engaging with the polls. I hope this was a good of a webinar for you guys than it was for us. And lastly, if you aren't already following us on LinkedIn, I highly encourage you to do so. So we'll have more webinars to come later down. Well, not this year necessarily, but in the next one. So do follow us there, and let's keep in touch. So thank you once again, and have a great day or great evening wherever in the world you guys are. All right, thank you, and bye bye.